Okay, so welcome all to this knowledge sharing workshop that we are organizing from the CETPartnership. We have two transition initiatives organizing this, the energy system integration and the industrial energy systems. And we are talking today about thermal storage in industry and its value and how it can foster energy system flexibility. So before starting, some practicalities. So we are in teams, so everybody can basically speak because we want people at the end in the discussion session to be able to pose questions. So please mute your microphone when you are not speaking. The meeting will be recorded. We will publish recordings of the presentation sessions, and we will also record the discussions, but that we will use internally for making a summary of the event. The online data declaration, as we always have, your name will be displayed in the list of participants. And for the questions, just quick clarifying questions of any of the slides that was presented to clarify, you can post directly after the presentation, but all the more profound questions that you may have, please note them and save them, and you can then post them at the end. You can use both the chat, but also you will be able to post to speak up in the discussion session that we have at the end. So we will have two presentation sessions and a discussion session today. So the first session will be looking from the energy system point of view on the future flexibility needs for power to heat and industry. And the second session will be more from the industry projects point of view, assessing the flexibility from thermal storage in industry processes. And we have the CETPartnership projects presenting. So then I think we are ready to start the first session. So I will give the word to Michele De Nigris, who is leading TRI1, Integrated Net Zero Emissions Energy Systems, and will take care of our first session.
Thank you very much, Hannele, and good morning, everybody. As Hannele said, I am Michele De Nigris, and I am the technical lead of the Transition Initiative number 1 of the Clean Energy Transition Partnership. The Transition Initiative number 1 deals with the integrated energy systems. What does that mean? Integrated energy systems are systems in which all the different vectors and all the different ways of producing, transforming, and moving energy are somehow integrated. The backbone of the integrated energy systems is the electricity, the power system, around which, why the power system? Because this is the system which is more easily put into a decarbonization state and pathway. And around the power system, all other systems can contribute, and of course can also develop their own pathways. So the power system as the core system of the integration of the decarbonized integrated energy system means that because of the ways of the intrinsic ways of functioning of the power system, with the decarbonization pathway in which more and more variable renewables are integrated into the power system. The term variable renewables means, of course, that the input from the renewables is predictable but not controllable. As far as the electricity system needs to be balanced in all moments, we need to have means to balance the electricity systems. These means are called flexibility somehow. Flexibility can come from the generation, flexibility can come from storage, different ways of storage, from the load, from conversion, and from markets, of course. This session is going to deal with the flexibility aspects as seen from the point of view of the integrated energy system. So it means that we are going to look at the needs of flexibility and how the different systems that are connected to the integrated energy system can offer flexibility, with the special reference to power to heat and to industry. The contribution from the different projects from these Clean Energy Transition Partnership that have applied and that are now operating under the TRI1 that you see listed on this slide are going to give us some hints, some solutions, some also some issues linked with the contribution of the different parts of the integrated energy system to the flexibility aspects and assessing also the flexibility needs. We will first start with a project called the Manœuvre, where we will discuss about flexibility assessment from the planning point of view. We will then go to Resilient, where flexibility from industrial process heating, which is exactly one of the themes of the meeting today. And finally, we will go to the CoPress project, where energy flexibility is assessed from a hypoxic air fire prevention system. So this is a very specific use case and application. So I will give the word to the first speaker from Manœuvre. We have Agustin Mingot from Solatom. Please, Agustin, the word is yours. Thank you.
Hello, everyone. I will start sharing my screen. I hope everyone can see my screen. Well, as I've been presented, I'm Agustin from Solatom. I'm working in the Manœuvre project, and I will be presenting the flexibility assessment and expectations in the European modeling and planning. First off, a brief overview of the Manœuvre project. The objective of this project is doing European general energy system simulations, but not just these simulations. A part of starting from a already stated general scenarios, we are also doing a smaller scope, more specific, even national simulations to try to achieve a more particular insight into some specific points of this system, to introduce this insight back into a more general elevated perspective, and in a bit of an iterative project, study the insights of these different points to better understand these general systems. So inside of this project, in Solatom and also Tiamat and different, we are working in a power to heat and thermal energy storage. Because at Solatom, we are a solar thermal energy for industry company, and we see this energy as complementary. I will not go into the specifics of the technical design of this equipment because other the following presentations will go into that, and I want to focus more on the importance of this design for the general simulation, for the future and prediction of it, because when designing a power to heat system, there are some certain characteristics that are intrinsic to the design. Any renewable energy has to define what peak energy output it can deliver, what total energy annual energy it will produce, and what would be the cost of that energy produced. We work commercially, and the balance of these points is the crucial avenue for installing this energy into a bringing it to reality. There are also some more specific points that we have considered when working with industry. When will you introduce the heat? Where? Are you going to generate steam and add it to the collector? Are you introducing heat into the conventional boiler? Are you boosting the water return from the condensate? Are you working with the direct renewable generation, or are you including a thermal storage? In this point, at least for us, is what we have this objective. We think the hybridization of the different technologies, both solar, power to heat, and thermal energy storage, is the best option because it introduces the biggest flexibility, control, and decarbonization capacity of all. So where does this all come into the simulation? Well, for example, this is real data of the Spanish energy system. A day we are studying for a design. I will not go into detail of the many different and important factors that affect this system because other presentation will do it. But what I want to say is that this is a minute-by-minute data set, and there is a huge variability in the values that will affect your designing of the power to heat system. I will assume we all have some familiarity with the system, but the potential, the economic viability of this power to heat system is determined by the electricity price. So you want to have an adequate control strategy to better use it. But this is only a day, well, a week in a energy system. And we want to simulate the energy system here on 30 years from now. It is not viable strategy to simulate at this level of detail for every single renewable technology we are considering. And as I mentioned, there are many specific points that you have to consider when designing an actual installation for industry. For example, this is the difference in shift working in different companies as a percentage of the total in Spain, depending on the energy consumed. This will greatly affect the capacity you have to use the energy you are generating. So how do we tackle this from the simulation point of view? Well, the first and most obvious one is simulating the flexibility of the energy system. It is one of the smaller simulations we are doing in Maneuver, studying how the energy demand and industrial demand will react to the shifting in energy prices and how that will in turn affect the energy prices itself. But there are also more intrinsic generalizations done to the simulation itself. For example, when designing, we do a simulation from the thermodynamic basic element of the point of the designing of the power to heat system. But at each step, you have to determine what are the the defining characteristics of that technology. I mentioned the ones that we have found are more important when actually bringing that technology to life, which is the capital cost of this power, the amount of energy or utilization factor you will actually have, and the cost of that all energy. But there are many more points to include. For example, this is an extract of a preliminary simulation.
Please mute your. Yeah, thank you.
Agustin, you are muted now.
Okay. Now can you hear me?
Yes, now it's good.
Okay, as I was saying, this is, for example, an extract of a preliminary simulation we are doing. We have already done some abstractions on the simulation. We have already characterized the thermal losses and the optical efficiency losses on solar thermal generation. we are using a typical meteorological year or more general characteristics for the solar and thermal losses generation, and we see an excess of this energy. At this point, you have to start including, well, what is your strategy for storing that? When will you use it? What power are you using? These are all very important decisions that are not clear for emerging technologies like solar, thermal energy storage, and power to heat. So you have to study different scenarios, but at the same time, you have to eliminate those scenarios when including it in a general point of view. So what the focus we are having in our project for the power to heat modeling is the quantization of the technologies. What I mean by this, we are going to characterize the technologies by themselves and as a hybrid system, and then introduce these different technologies into our energy system modelization. We will have a thermal concentrated for industry. We will have a thermal concentrated for industry with storage, a power to heat technology, and a combined power to heat, solar, and energy storage system. How will we do this? Well, for example, in the solar with storage, it is a strip of all the different storages you can include, considering different values. Well, for a determined solar power, what powers can you give to your storage, and what capacities can you give it? When do you start hitting diminishing returns with increasing storage capacity? What are the most common use cases for this technology? And with all that, you will decide what is the defining configuration for this technology, or most representative. I think it's better for that. And after doing all those for the different configurations of the technology, you define the characteristic. What is the capacity cost for this technology? And using representative days and representative consumptions and expected changes on those, you introduce it to the simulation, and you can get a relatively representative working of hour by hour of these points of view. So what are the challenges and what are the benefits of doing this reasoning? Well, as we will see, there are many different ways to do power to heat. For example, in our case, we are considering using a directly thermal resistance, but heat pumps offer a great deal of efficiency. You have to quantify what is the limiting factor for the entire power to heat technology. In this case, it's electricity, but you have to define this in a way that you can introduce it in your system. Get a dispatch power inside the simulation. What is the advantage of the disadvantage of each specific configuration you could do in a real case construction? Is it worth it to introduce the heat directly into the process, in the collector, in the preheating? And consider all these options, study them, and introduce them again in the general system so you can again elevate those results to a general European point. Is it worth to hybridize? Well, that is a big question for a power to heat, thermal energy storage, and solar system. Is a complex interlocking system, and you have to we are going to build a prototype to actually know how it behaves to better characterize it. So, but in the end, we think it is worth it to do all this work in defining each single point and building up from it onto a bigger system, because with that, we will actually be characterizing a very powerful technology for flexibility, and with how will I say, with complementing simulations from other parts of the project that are simulating the flexibility of industry from the other side, and all the different, because with many different simulations of detailed points of the bigger side, of the bigger system, we get a more detailed flexibility of this system. So you can actually introduce the benefits of these model simulations into the bigger general simulation. So as a conclusion, what I want to say and the ideas I want to bring is it is not only a matter of simulating this flexibility. The simulation itself needs flexibility, and the simulation itself needs to account for the flexibility of the systems that it is simulating. It is not only a matter of determining specific values because 30 years from now, those values won't be the same and you are making guesses. You need to be able to account for the changing circumstances to be able to make usable predictions for the future. And well, that's how I want to finish my presentation. I think there is only specific questions, or we will go to the next presentation.
Thank you very much, Agustin. Your last message is very strong. So you need flexible simulation to flexibly simulate flexibility in the system. I think.
Yeah, I think it's a very nested idea, and it is difficult to explain in a reasonable way. But I hope I have done a good job of doing it.
You were very clear, and I think the system that you are developing is quite interesting also, especially if we look at scenario analysis, because at the end, the planning and the activity that you are looking at is essentially linked with the scenario analysis. And of course, scenario analyses are not predictions, they are what-if simulations. So the idea is, of course, very, very much to try to understand what will happen, what would happen in case of availability of a given source, and related, of course, not only to the technical aspects, but also to the cost aspects, so capex and the cost of energy. So I think you explained it quite well, and I really think this is a good basis also for the next discussion. So thank you very much. Stay connected, and for the participants to this meeting, please, unless you have very specific and very to the point question on one or more of the specific slides that Agustin has shown, we will keep the questions for the discussion part in the third session of this meeting. If there is, I don't see any hands raised from the audience now, and I think we can go to Tobias for the second presentation of the Resilient project. Tobias, the floor is yours. Thank you.
Yes, thank you very much for the introduction. I'm very happy that I can present a few first insights, results from the Resilient project and what we found out in relation to industrial flexibility and transition. And yes, my name is Tobias Fleiter. I'm working for the Fraunhofer Institute for Systems and Innovation Research in Karlsruhe. Working on industry transition and energy systems modeling since quite some years there. What I'm presenting here is from the Resilient project. Of course, this is work done by an entire team of colleagues. Also, Khaled Aldabas, Benjamin Lux, Wolfgang Menner were involved here. And I want to show you a few results from our energy systems analysis, especially looking at flexibility in process heating, taking a look also at the long term beyond 2035 towards 2045, 2050. Yes, going into before going into results, just a quick overview of who we are in the Resilient project. So the entire project is coordinated by the Technical University of Berlin, the group that is actually working on the Pulsar EuroSec model. But there is a number of other universities and research institutes involved working on the different topics. And we also have partners involved that work more on the on the implementation, on the dissemination side to engage the stakeholders and work on the 3 case studies in the regions that we look at. So that's broadly speaking the setup, and but I don't want to speak too much about what we have planned and how the project is structured. I rather want to show you some interesting first results. We have, before doing so, motivation I think is clear. In the past, for such kind of studies, in order to motivate them, we have looked at results from system models for future years, etc. So now we are actually at a point where the transition is really ongoing and quite upscaled already. So we can simply look at the past. What we see here is for Germany. This is a summer week this year, not too long ago, and we see, and the red line is the power prices, wholesale prices, and the areas are actually is actually the generation. So in green from renewables and in gray from fossils. What we see, of course, in the green area are these typical summer peaks with a lot of installed PV capacity, and we can actually see that the prices are following these generation peaks. So we typically have price peaks in the morning, but even more in the evening when demand load is still high, but PV generation already is down. And we also more and more see negative prices. This often happens at weekends when the load is quite low and there's a lot of generation from PV happening. So then, of course, with this, the question about demand side flexibility, industry flexibility is on the table. And let's now look a bit at what we looked at. First of all, it is important to also anticipate the change that is expected, or that's likely to happen in the structure of industrial energy demand. So while today we've got an electricity demand mostly used for mechanical energy, and process heating is nearly fully supplied by fossil fuels, mainly natural gas. This is expected to change dramatically in the coming decades. And hydrogen and electricity are expected to take a strong role in that. So we've got we see here a scenario for Germany. So what I actually have results for Germany in this presentation, and we can discuss also applicability and for other countries then in the discussion later on. So we see here that there's a substantial demand for hydrogen from the kind of transition to climate neutral industry, going up to 300 terawatt hours, but depends a lot on what the chemical industry is going to do and what kind of feedstocks they're going to use. But also for electricity, we see an increase in demand, and that actually in all scenarios. And the main driver here is process heating. So using electricity for high temperature process heating, but or a lot, mainly for medium, low temperature steam generation, where technologies like electric boilers are already available, where high temperature heat pumps could be applied. And we see only for Germany an increase by 100 to 150 terawatt hours of electricity for direct process heating. But of course, also the hydrogen needs to be generated. If this is done via electrolysis, which will have a very high share, this generates a very substantial additional electricity demand. So this is the setup, the background for the systems and systems results that we see very soon. So now looking more at the system perspective and at the energy system model. Here we can see this is a classical dispatch graph where we have the supply on the upper side and the demand, the load on the negative side. Also here summer week. Now it's not the year 2024, but it's the year 2045 under the assumptions I presented. We see again these PV peaks. They are a lot higher now. They even touching 300 gigawatts. Or the entire peaks in Germany in this climate neutral system. We see a bit of imports, not much wind generation, so a very heavily PV dominated week. And there you see already how much flexibility already is in the system, because the load follows very much these PV peaks. There is, of course, also curtailment, but there is a lot of flexibility from hydrogen generation via electrolysis. There's also a lot of flexibility already from vehicle to grid. And of course, many other flexibility sources. So to summarize a few figures, overall demand goes up by roughly 140% on top. So from 500 to 1,200 terawatt hours. Installed capacity from wind and PV increases by 300% to more than 500 gigawatts. And also the load, as you see here, is going to a maximum of 300 gigawatt. And of course, yes, this has then also strong requirements for flexibility, but also potentials for kind of new business models. We looked at flexibility from classical or from processes that are already electrified today. So it's mainly mechanical energies, also maybe some cooling processes here and there. And we come to a total aggregated figure of 5 gigawatt of load that could be shifted for a duration of about 4 hours. So of course, if you compare this to the total load and generation numbers that go up to 300 gigawatts, it is a small share. So that's why we think, of course, it can play a role, like the flexibility in these kind of already electrified processes, but it's also important to have a realistic estimate of the overall potential on the energy system. What did we do? We then looked more at the potential of flexible energy supply, heat supply, instead of making the entire process chain flexible, just making the energy supply flexible. And here we especially looked at steam generation and at steel production. Before that, still a look at how does it. Yeah, we also could look at different weeks. Here's a winter week, but I think that does not add too much now. So let's look at this flexibility in steam generation. So as I said, today we have steam systems mainly supplied by natural gas in most countries and most industries. And here you can see on the left side how the supply of the entire steam demand in up to this temperature level of 200 degrees in Germany in industry is in this very scenario distinguished between energy carriers. So we see for the year 2035 still a high importance of natural gas, of methane, by more than half of making up more than half of steam supply. But we also see a high relevance of electricity already, which we today hardly see in steam supply in Germany. And towards 2045, we have even more a higher importance of electricity, and then some remaining hydrogen demand. So that's first the overall energy balance in a very aggregated way. And then at the right side, we look at the year 2035 at the top chart, which shows actually the supply of steam by type of technology for every hour of the year. And we included 3 technologies here, which is electric boiler, heat pump, and then CHP for 2035, natural gas CHP unit. And interestingly, we can see that the system model uses both the heat pump and the gas CHP, and operates according to renewable generation, basically electricity prices in the model. We see that the blue areas are more densely during winter times. So we typically we have higher electricity prices in Germany in this future year during winter, because higher demand for heating and lower solar generation. So we see more use of the gas CHP in winter and more use of the heat pump during summer. And we don't see the electric boiler. So the system model, which actually optimizes or minimizes the total system cost, always prefers a higher efficiency from the heat pump than the lower capex and lower efficiency from the electric boiler. And now it's the question, this was just for 2035. So how does it look like in the long term? And the graph on the bottom then shows you the year 2045, which where still the CHP unit has some operating hours. Heat pump in total gets even more important. But in this cost optimal solution, there is also a role for this then hydrogen based CHP in the long term. And this is quite interesting, because on the one side it shows how the transition could happen, kind of adding to today's gas-fired, gas-dominated process heat supply, adding first maybe stepwise electric electric heating units like heat pumps, but also electric boilers, and increasing the capacity over time, and then simply increasing the operating hours according to prices and availability of renewable electricity. But also that being a model that works in the long term, when the hybrid system is then not natural gas and electricity, but hydrogen and electricity. So this brings in a lot of flexibility to the system, a flexibility that is not really limited for a certain duration as we have seen for the load shift earlier on, and a flexibility that does not require to interfere in the different production processes, etc. Actually, the systems that are using the steam, they can just continue producing as they would today. So these, I think, are two important advantages. Yes, maybe to dig a bit deeper into the background, that's of course then the electricity prices in the system model. What you see here is that we cannot say for a certain year that either electricity or hydrogen is more expensive. We actually see an interesting pattern where mostly electricity is cheaper than hydrogen during summer when we've more PV generation, and hydrogen on the other side is often cheaper than electricity during winter, when, for example, hydrogen is also used for electricity generations in times of low wind and PV production. And hydrogen also, this model also uses large-scale hydrogen storage for seasonal storage, so hydrogen can be better stored for winter operation, and so has price advantages during winter time. And that of course is the basis or the explanation, or one of the explanations for the operation of the hybrid systems we've seen a slide earlier on. Very quickly, we also looked at or we did a few first test runs for flexibility of hydrogen and natural gas in steel generation. As you might know, many steel producers are now planning or even started to replace current coal-based blast furnace plants by direct reduction plants. And these direct reduction plants, they can use basically methane, natural gas, or hydrogen. They can also relatively flexibly blend both, so they could use hydrogen according to prices and availability, which is especially important during a time when the hydrogen system is actually being built up and still not fully functional, when prices might fluctuate heavily and availability also is not always as good. So we also here we developed a scenario for the future uptake, and we see an interesting pattern. We see that actually, so this is the production actually the energy demand for the production of direct reduced iron over 1 year, 2035, and we have we've given the model one side condition: it should use at least 50% hydrogen over the year, but can choose at which hours, or how the operation schedule is. The schedule is then actually optimized, and we see that the this cost optimal solution has during winter times a full use of natural gas, and then during summer times, kind of strong use of hydrogen. Also reflecting what we've seen earlier on about the electricity or the hydrogen prices. And this, of course, this also is a kind of seasonal storage. So it provides, this strongly seasonal profile. If we then would have time to look at the implications for the hydrogen system, we would see that the demand for seasonal storage of hydrogen is reduced by roughly 1/4 for this year 2035. So as I said, especially when the hydrogen system is still being built up, this provides a lot of flexibility to the system. And yes, very quickly, the core results. First, I already mentioned future system will be highly wind and PV dominated. Flexibility will become more important. And then more specifically, we see that hybrid systems for process heat generation, electric heating and CHP, or in the future, electric heating and hydrogen CHP are very cost efficient and beneficial to the overall energy system. And yes, probably initially heat pumps or electric boilers supplementing gas-fired CHP or gas-fired boilers, and then in the future upscaling it, increasing the share of generation from the electric generators. Yes, and for the steel sector, but also applicable to other high temperature process heating, we see that this upscaling of hydrogen use, the uptake of hydrogen use, should be flexible in the transition period, so in order to provide flexibility to the build-up of the entire system. And with this, and of course, in these directions, we continue now in the resilient project methodologically wise. And with this, I would like to thank for your attention and look forward to the discussion.
Thank you very much, Tobias. Complex and very complete presentation of different scenarios as well, and also a long-term scenario, which I think is of high interest and high importance. We have really seen also the opportunities and the challenges of flexibility using we can say different technologies for somehow power to heat, and also for the direct industrial application in the reduction processes. We have, I think, the 1 or 2 questions in the chat that probably we can perhaps mention. I think the first one from Gerfried was more dedicated to the first presentation, if I understand correctly, about the flexibility mindset. A second question, probably we can bring this question then to the general discussion aspects. And a question from Esther that seems to be already answered by Gerfried himself. If I understand the presentation right, the CHPs can provide steam at 200 degrees, so they have to provide heat at a higher temperature. I wonder if there is a CHP able to do that, or is the simulation assume certain technological development that today's do not exist? And the initial response from Gerfried is yes. So I don't know if you agree to this, and if you can perhaps give additional hints about that on the essential technological capabilities of CHPs and heat pumps. And heat pumps to high temperature heat pumps to give this level of temperatures.
Yeah, so maybe briefly a few words on that. I'm not sure if this question also really relates to CHPs only or to heat pumps, because typically you get this question rather for heat pumps.
Yeah, this is why I converted it also to heat pumps, I think.
But still starting with CHP, gas-fired CHP are the kind of classical solution to provide heat, for example, in the paper industry, which is the one main user of actually steam in this temperature segment, 100 to 200 degrees Celsius. Yes, don't take the 200 as a too exact fit. So it's really about the broad range of steam need in this below this temperature. So yes, natural gas CHP is the standard solution for this in many industries. But when it comes to heat pumps, of course, this is not so standard. There's a lot of development in high temperature heat pumps, and we also see many applications in the food industry, for example, already where temperature levels are a bit lower. I'm not yet aware of large-scale installation in the paper industry, for example, which would maybe relate to your question. If anybody knows, it would be very interesting to hear that. So yes, there is some technology demonstration and technology development still needed, but I guess as we've shown 2035, so for the next, I think hopefully earlier than 2035, this will become available. I would say so.
Thank you very much.
And it can also be a combination of heat pumps with electric boilers, where you work with certain temperature lifts of the boiler and the heat pump, etc. So, yes.
I think we can bring this to the discussion part. One perhaps a quick comment is, can you comment on the ratio of solar over wind in your simulations? I would have also liked to ask you this question because I see that the contribution is very, very strongly on solar, and I would have expected it to be the wind to be more present in your simulation somehow.
Yes, but basically these the assumptions follow the targets of the German government for deployment of PV and wind by 2045. And I think the PV target is somewhere, in total we have a capacity of 570 gigawatts by 2045 of wind and PV. And I think PV is somewhere around 300, maybe more. I would need to check the exact number. But yes, you can see here that there's a winter week. So this also shows a very strong wind generation.
Yes. Mm-hmm. Okay, great. I think we can come back to this. I see there is a hand raised from Julius Weiss. If there is a quick question, then we can go to the third presentation. We are a little bit ahead of time. We are a little bit late.
I think it's not a quick question, but I will raise the question and we can see if we can discuss it later on.
Okay.
Thanks, Tobias, for the interesting talk. For me, it would be interesting to hear a bit more on these price scenarios for the future hydrogen and electricity prices, and which kind of grid fees did you consider and the formation of the prices on the market? Is the grid fees considered, and what is the spread there? And the other question I had when looking at this is like, did you consider a European energy exchange in your simulations, or is this just Germany isolated, basically, that you try to fulfill the demand of Germany in your
Maybe a few quick words. I mean, it's always problematic to show in such a short time results of a complex modeling study because you cannot present all the assumptions. But this was a European-wide calculation, and one key flexibility is transmission between the countries, transmission of hydrogen and electricity, build-up of hydrogen storage across the continent. So there's actually a lot of solar and wind deployment at the cheapest locations in Europe, and then also transporting to countries like Germany with less good potentials. So yes, and this drives a lot the overall results. And quickly on the price, I mean, it's maybe called shadow prices here. It's maybe a bit more the cost actually. So this is not the kind of end user prices or something. It's more really the relation of the cost of these two energy carriers. So they have it's just to rather to compare within the system logic what is how is their competitiveness at certain points in time. But it needs to be translated still when you want to say something about what would be the electricity or hydrogen price that industry or households could procure.
And
we will come back to this during the general discussion if you accept, please. So we can go to the third presentation from COPRES. Adrian, are you connected? And you're going to speak about assessing energy flexibility from a hypoxic, difficult to say, air fire protection system.
Yes, let me bring up my slides. So hello everyone. With this presentation, we're coming back from the continental or national scale and the gigawatt scale to the very local kilowatt scale flexibility. What I want to do is talk about how we're looking into using an industrial fire prevention system for energy flexibility, and that's in the scope of the COPRES project, as was already said. Very quickly, my name is Adrian. I'm working for BKW, a Swiss-based energy company, or originally it was. Nowadays, we're more of a infrastructure services company in the building and energy domain. And we still have our headquarters in Switzerland, but over 200 subsidiaries all over Europe. The COPRES project, very quickly, is an international collaboration between the four main partners that you can see here. And the goal of the project, very broadly speaking, is to enable consumers with distributed energy resources to actively contribute to grid operations and participate in energy markets using their flexibility. And part of the project is also to facilitate this by developing an open technology platform. But now, the topic of today is that very specific source of energy flexibility that we have identified on our Swiss pilot site for the COPRES project, and that is the fire prevention system. I'll quickly go through the concept behind it and the context of our COPRES pilot site in Switzerland, before then sharing some initial estimates on the flexibility that we expect to harness from the system. So all of this is still ongoing work. What I'm presenting are very rough estimates, but that's okay because we're still primarily assessing the technical feasibility and the viability of that specific use case and that specific asset that we're looking at. Now, hypoxic air fire prevention. The fire prevention system that we want to leverage for flexibility is based on the very simple principle that you can put out a fire by starving it from oxygen. Moreover, if you are in an atmosphere that is sufficiently low on oxygen, a fire cannot spread. It may not even break out. And therefore, a very effective fire safety measure is to keep high-value assets in a so-called hypoxic environment. So examples for this, where these systems are used, are especially data centers and warehouses. Warehouses that, for instance, store flammable objects. There are different ways to create such an hypoxic environment in a closed space. The process that we consider uses compressed air, because with compressed air you can drive a process that is called pressure swing absorption. And with this process, you can separate oxygen from the air. The separation, at least for the sake of fire prevention, does not need to be perfect, but the important thing is that you get out hypoxic air that is sufficiently low in oxygen. Because this hypoxic air is then pumped into the spaces that you want to protect from fire. So these protected rooms, they nevertheless, they have doors, they have openings, and therefore you have leakage of the hypoxic air. Or more precisely, you have oxygen or high oxygen air or ambient air that will penetrate back into the space and raise the oxygen concentration again. So what you'll need normally are oxygen monitors in the protected volumes and a control unit that will keep the oxygen concentration in those protected rooms and warehouses at a specific level. And this is where you can probably guess that this type of creating a hypoxic atmosphere is very similar to thermal storage. Namely, you can control the oxygen concentration in a room similarly to controlling the temperature. You can drive down the oxygen concentration by using, in this case, electric energy to produce compressed air, which you then can use to create this hypoxic air. But if you don't do that, if you don't produce the hypoxic air, the O2 concentration will slowly rise again. And in the same way that you can give a desired temperature range to a thermostat in a room, you can have a range of admissible oxygen concentrations. And here the constraints that you have are, on one hand, that the oxygen concentration cannot be too low. Otherwise, it poses a safety risk for the people who work in that room, even if it's, or usually it's just for maintenance, but still the room has to be accessible for people to do work in there. And on the other hand, of course, if the oxygen concentration is too high, your fire prevention is less effective. But nevertheless, you have this interval of oxygen concentrations that you can play with, that you can use to provide flexibility. So far about the general concept of this hypoxic air fire prevention. Now let me give you a quick overview of our CoPress pilot site in Switzerland, where we have such a system that we can control, or at least partly. The pilot site is part of our use case 1 of the Swiss part of the CoPress project, which aims at looking into how we can increase the profitability of local energy systems by means of intelligent building automation. And for this purpose, we're partnering with an energy planning company that is itself a BKW subsidiary. And this energy planning company, they have one client that is a large logistics company. And they have this warehouse complex in Switzerland that has a pretty complicated energy system. However, they are very open to test out new energy management techniques that can bring down their energy costs. And in particular, what we are interested in the context of corporates, but what also is of high interest to this client, is peak shaving of their electricity consumption. They want to optimize their self-consumption from their locally produced PV power, and potentially they want to be able to sell their flexibility as ancillary services, especially secondary and tertiary reserves. But this will happen through an aggregator, because by themselves they're not large enough to sell that on the wholesale markets. And to harness these opportunities, a number of energy assets can be controlled. Among others, as I mentioned, we have the PV system. We have the fire prevention system that I'm going to talk about more in a minute. And we also have a fairly sophisticated heating and cooling system consisting of heat pumps, recoolers, but also thermal tanks that can act as storage. Now, all of this looks very interesting from a building control point of view, but we have to remember, and in some cases we learned the hard way, that we are working with a system that is operational. It's continuously evolving, so there are all the time new assets installed, another heat pump, another air compressor. And sometimes some of these assets, they go out of operation because of unscheduled maintenance and so on. What else we're facing is that a lot of these energy assets, especially the control side, these are black boxes. We don't know exactly what's implemented, how are they going to behave. And this, of course, also makes our work here more challenging. And finally, we are under no circumstances to interfere with the business processes, meaning the logistics operations, because that's what creates the revenue for the client, for the asset owner, in this case. So, given this situation, we decided to focus a bit on the fire prevention system, because we have a very good idea of what it does. It's fairly isolated from the rest of the whole local energy system, and it is something special that you don't find on every industrial site. Now, with that, let's dive a bit deeper into the specific system that is installed on site. Namely, we have 4 air compressors in operation. Soon there are going to be 2 more, and all of them, they feed into a compressed air network that spans the entire complex. Now, the air separation units that constitute the fire prevention system, they're not the only consumers of this compressed air. We have pneumatic machinery and doors that also consume some of this compressed air. And these enter our view of the system as a source of noise, as you'll see in a moment. We have a number of measurements here. Most importantly, the oxygen concentration, the average oxygen concentration in the storage modules, and also the aggregated electricity consumption of the air compressors. On the control side, the things look a bit more reduced, because we essentially have control over one single storage module here. Might be a second one soon, but still, we can control one set point, and even that we can control only in a binary fashion. We can set the set point for the O2 concentration at a higher value or a lower value, and that's all we can do with this system. Nevertheless, in the last couple of months, we were able to collect some high-quality data that has enabled us to better understand the system behavior. We now have one month of usable data, which is not a lot, but which is representative of the general complexity of working with this real system in this context of having an actual industrial partner that lets us control their assets. So we have 1 month of high quality data. Here you see 2 weeks of that. During these 2 weeks, we have done trial activations of the system, meaning we've switched between the 2 set points for the O2 concentration. And what we see here at first sight is that indeed the oxygen concentration in the protected volume rises or falls in response to the activation signal, but then also oscillates around the set point. And that is due to probably a deadband controller that is part of the air separation unit. That's for the oxygen concentration. However, when we look at the power consumption from the air compressors, things look a bit less clear. And that's in particular because we have these pneumatic loads that also consume pressurized air. So it's not just the air separation units that require the air compressors to run. When we zoom a bit into the individual switching events, we actually see that the electricity consumption does indeed almost immediately respond to the activation signal, but the response always depends a bit on a number of factors. And what we also nicely get out here are the rates at which the oxygen concentration falls when we activate the lower set point, and we were previously at the higher set point, and how fast the oxygen concentration will rise again when we switch off the system, being we switch to the higher set point. So just looking at these signals then and getting these insights, we are able to have a very rough flexibility estimation on this system. And one important thing that we noticed is that we have to distinguish between the system during operating hours, so when people are working in the warehouse, because then you have a lot more doors opening, doors closing. So that means you have a lot more leakage of this hypoxic air. That in return means that you have a higher average consumption to maintain your desired oxygen concentration, which on the flexibility side means that you have a pretty good down regulation potential, even though it's just for a few hours, because the air compressors have to run soon enough to catch the O2 concentration from rising too much. Outside of operating hours, the situation looks very different, because there the leakage is very low. So the air compressors on average, they have to work less, meaning that by trying to completely switch them off, you're not reducing consumption by that much. However, you could sustain it for quite a long time. On the other hand, your upregulation potential is then much higher, even though again for a shorter amount of time. Again, so these are very rough back of the envelope calculations based on half a dozen activations. So these numbers need to be taken with a grain of salt. But nevertheless, they're better than any estimate that we had before, and they're a good basis for the discussion with the asset owner and the other stakeholders at the pilot site. And with that, to summarize, what we've done in the last couple of months is really establishing the viability and the technical feasibility for using this fire prevention system on the pilot site for energy flexibility. And as trivial as it may sound, we are confident because our control actions, they have a measurable and by all means foreseeable effect. And that's not something that comes for free when you're on site working with an existing asset of which you don't know exactly the internals. So currently what we're doing, we are working on a proper well-fitted dynamical model that we can use for control and forecasting. But more importantly, we need to go back to work out with the stakeholders on site what exactly they want this flexibility be used for, be it peak shaving, self-consumption optimization, or provisioning of flexibility, and how we can best leverage that flexibility. And with that, I close my presentation and thank you very much for your attention.
Thank you very much, Adrian. Very, very interesting and unconventional applications. Quite interesting. Just a question which has very little to do with flexibility, but the operators inside the warehouse, do they operate with the oxygen masks and things of this kind? Or I would expect that if they don't, they are very lazy inside. But
I don't know. I've only been informed of the admissible oxygen concentration, the lower end. How exactly it works, and what the safety precautions are, I'm not aware of.
Probably this is a very good application of robots and artificial intelligence.
Yeah.
Thank you. Thank you very, very much. Hannele, I am sorry I am a little bit late with my session, but you gave me the permission to go a little bit further with respect to the scheduling, because then we have some time for discussion afterwards. So now the word is yours. Thank you very much, Hannele.
So as a second session, we are looking at thermal storage in industry processes. We have two projects looking at that, and we get presentations from them. And as for the introduction, so my name is Hannele Holtinen. I work for Click Innovation in Finland and help coordinating the integrated industrial energy systems focus area in CETPartnership. I also work for IEA Wind, leading a grid integration research collaboration there. So flexibility is very much my expertise, as coming from my previous long experience working for the research institute VTT. So as to introduce our second session, so now we're talking about really flexibility from industry, and we have already heard it does exist already today, but on a smaller scale than what we see in future scenarios than what is needed. So it will be a huge change in energy transition and also opportunities for future, because it is very crucial that the industry, and especially the new industry, will be flexible for wind and solar dominated power systems. We have a new person attending that has his microphone on, so please mute. Thank you. And then the big question is, what is the value? How can we incentivize this flexibility from industry? So with this, I will give the floor and screen to the presentations. So first we will have the ISDEMO project. So it is actually presented by Carlotta von Daten del Valle. So please, you can try to share your screen. and give the first presentation. Thank you.
Perfect. Thank you. Can you hear me and see the screen
Yes.
now?
All is very well.
So hello from my side. My name is Carlotta Fontan del Valle, and I'm from the Fraunhofer Institute Umsicht in Oberhausen in Germany. And today I will be talking about a part of our project within the Transition Initiative 6, which is the project ISDEMO, and the integrability of the high temperature thermal storage for steam in different industries. So just an outline of my presentation today. I will first be introducing the ISDEMO project and then go on to how this specifically latent heat storage can be applied into the different industrial sectors. Take a closer look at one of our main case studies, which is the brewery, and then connect it to today's topic of flexibility and our aspects of it. So the ISDEMO project is also an international collaboration with partners from Spain and Poland. And our main objective is to develop a metal-based latent heat storage for high temperature applications, so between 250 to 500 degrees Celsius, with main focus on industries that utilize steam as a process medium. And the storage itself is currently on TRL5 and will be developed to TRL7. But as we are an applied research institute, we try to also look at the industrial side of it. So alongside the actual technical development of the storage, we have specific case studies for the implementation of this storage into the industrial systems. Also relevant for today's topic of flexibility is that the storage will be charged via steam and will be charged via electricity and discharge steam. So here you can see the work packages. So there are some project partners that are concerned with the development of the storage and the installation of the test site. Us particularly, so my team focuses on the work package 4, which is the conceptual integration of the power to heat and storage device in the 3 industrial use cases, which are pulp and paper, food and beverages, and the chemical sector. So what this means is that from these sectors, we try to create a generic, or not a generic, but a more like an example energy system using data from our industry partners within the project, but also just literature research. And then this will be dynamically modeled and simulated in a Modelica in the software Daimler. And the thermal storage will be integrated in here. So also part of this applied research theory is that apart from the pure technical development where we get information on the storage, we also feedback information on the actual industrial requirements for the storage and what we would suggest to implement in the storage development. So I have brought with me today an overview of the different temperature ranges for the different industrial sectors, so you can maybe get a better understanding of how these industries typically operate. And I have circled the industries that we have taken as use cases for this project. So as I said, chemicals, food and beverages, and paper. But the temperature range up until 500 degrees is marked in green. So the first 3 bars that you can see on the left. The industrial partners that I've also briefly talked about are for Paper and Pulp, the trade association of the Rhenish-Westphalian paper manufacturing industry in Germany. For food and beverages, one of our main partners as the demonstration test unit will be installed there is the Bitburger Brewery Group. And for chemicals, our Polish partners have partnered with the Sanok Rubber Company, so a rubber manufacturing company in Poland. Just briefly, latent heat storage and why I've shown this temperature range as well, typically utilizes the latent heat, which is the heat from the phase change. So when going from solid to liquid in our case, so the melting process of these installed phase change materials, in our case, these metal alloys. Hence the temperature at this point is stable at the melting temperature. Hence it is typically used for processes that have a similar temperature range. The high temperature latent heat storages are, however, less developed than sensible heat storages in that temperature range, but they offer other benefits, as I explained, the process stability and efficiency, as the temperature during discharge is relatively constant, as well as the steam pressure that we can discharge. And due to the higher storage capacity because of the material, it requires less space for installation on site. Generally, there are different options for charging and discharging thermal storages. In our case, the thermal storage will be charged electrically. Because there is no clear or direct advice on which storage to apply to which industrial sector, I've just written out a few of the aspects that you can consider, or we can consider, in the case of finding the suitability of our storage to the industrial sectors. So as I mentioned, the storage is both a steam generating as well as storing device. So it can be applied to industries that utilize steam for their production processes, such as drying in the paper industry, boiling in the food and beverage industry, etc. Also, generally, storages, thermal storages are highly considered for all the batch processes. So processes that are done one after the other instead of the mass production, which is done simultaneously. In this case, you can store heat for later usage. So these are processes typically occurring in the beverage industry for dairy processing and pharmaceutical products such as soap and biotech, as well as other manufacturing. And then, as I showed before, the temperature range is also indicative of the suitability for the storage. So you could match and overlap this temperature, this operating temperature of the storage, to the industrial sectors, which I've just picked a few, which was chemicals, food and beverages, paper, obviously, but also rubber and plastic, pharmaceutical, etc. And due to the fact that this storage is supplied via or charged via electricity, another consideration on choosing this storage for an industrial application would be the fact of having renewable energy integration on site. So if you're looking at the flexibility options of combining these sources of power and reducing the cost here. On to the case study of the brewery. I have depicted a general brewery process. The main aspects here are that it is a process utilizing steam as well, typically. And in the image, you can see little flames indicating the process steps that require heat. and the storage would then be connected next to the conventional steam generating devices to supply the entirety of the system, because there are other ways of connecting between these process steps as well. And on the right, I have a very general Gantt chart of the brewery batch process, so that you can see the time that it takes for the different process steps and the big difference between these time steps. So when generalizing a system like this, one of the main considerations is also looking at how big the industry is, in the sense that how many simultaneous processes of the different steps can be done, which changes the energy demand. So alongside with the project, we have then tried to generalize this system as one of the industrial energy systems. So in the first step, we have used Bitburger data to integrate the model of the storage so far and analyze how it would fit in there. But now in this phase, we are creating this a general brewery energy system with its demands, which is done by reducing the components also from the Bitburger system to the main ones that we can find in other breweries as well. And this is also validated and looked at through our literature research. And then through methodologies such as scaling, we then remain the confidentiality of Bitburger data. And in the last phase is, as I mentioned, the actual simulations of the thermal storage in that system. So this is what it would conceptually look like. Basically, I am comparing here the integration of the storage to conventional methods, as well as relatively conventional renewable integration methods into the system. So I have the latent heat storage here in the center with the two components, one which is a storing component, one which we consider like a direct steam generation, so the power to heat component of our storage. And this supplies steam to our generalized industrial energy system, where the process steps are basically modeled as heat exchangers with a time series, temperature, pressure, and already have their efficiency measures dynamically simulated as well. And on the other hand, yeah, all the conventional possible methods, which is starts with the conventional boiler for steam, which are, as we heard in the previous presentations, still mainly produced by fossil fuels. But also I have added also an electric boiler powered by renewable electricity as an option to defossilize that part, all combined with a backup steam generation, which is also very common in this industry. But another way is also the use of a CHP unit in the combination with a peak load boiler, which are all typically fossil-based. And on the electricity side of it, also for the charging of the thermal storage, would be the renewable energy integration on site, so photovoltaic and wind installations on site, as well as renewable electricity from the grid. And in the sense of flexibility, looking at the different things that we could take part in from the power market. So looking at having different fixed prices, but also the participation in the spot market, so day ahead market and intraday market. And now on to today's topic of flexibility. I have taken here an image on the definition of flexibility from one of the dissertations at our institute. And here we have two possible ways of looking and quantifying flexibility. So in the first application, A, that you can see here, high flexibility is associated with a high deviance or high possible deviance from the reference operation. So a system is considered flexible if it can perform a lot more different to the standard operation that it has. And in the flexibility operation B, flexibility is defined as if a system is more flexible the closer it gets to the path that is required after an external signal is given. This form of definition I would associate more with the actual development of the storage. So what the work packages 1, 2, 3 are currently doing, because I associate it with what storage duration do I have and what is the response time. So for charging and discharging, as well as for the steam generation, what is the efficiency of the storage and what control options are in place, as well as how the connection to energy management systems look like, but also things such as the actual geometry of the storage and the sizing influence this kind of flexibility. The flexibility that our team is looking at within the project considers the aspects that would apply more to the first operation, which I show here a bit more in detail. So one aspect is the adaptability to variable production cycles. So we've talked about the brewing process being a batch process, but as well it has some seasonal peaks. And then also the topic of peak shaving is relevant in this analysis. And the storage, and this is also on the topic of exchange between the different work packages. The storage is supposed to be modular, so we are looking into what size and scale makes sense for the industry in this case, but also the aspect of the integration of renewable energies, specifically with the volatile sources, solar and wind. And obviously the main topic of reducing cost when integrating it or when looking at flexibility in energy efficient systems, as well as the market participation aspect. Oops. So all these aspects are then quantified looking at different from a systemic, ecological, and economic point of view. So systemically, we're obviously looking to increase energy efficiency and also already have the increased weight heat generation integration in the system. Ecologically, a reduction of fossil fuels is obviously the aim, as well as an increased lifetime through good operation, especially of charging and discharging of the storage. And economically, when looking at storage, we often talk about the levelized cost of storage, so reducing that as well as reducing general costs for electricity. And that is, if I can just come back, the objective here as well. So reducing all these fossil fuel aspects, and reducing the cost, increasing the efficiency of the system. And that would be all. Thank you so much for your attention. And I am happy, alongside with my team lead, Matthias van Beek, to take questions in the panel discussion later.
Thanks, Carlotta. Very nice presentation for your your project. So there was actually one question specifically about solar thermal, but Matthias was already answering that in the chat. So it's not in scope of this project, but it is definitely an emerging topic for other projects, and very nice development there. Okay, so let's move now to the next presentation, which is our last presentation today from Julius Weiss. And this is from the Locomosa project, also looking at thermal storage.
Yeah, can everybody see my screen? I
Yes,
guess so.
yes, it's working
yeah,
nicely. Thank you.
Thanks for the introduction. Yeah, my name is Julius Weiss from Fraunhofer ISE in Freiburg, Germany. And I have the pleasure to present some work of ours within the Locomosa project. And topic of today would be power to heat and energy storage system, system layout and operation strategies for process heat based on the day-ahead market pricing. So few words on the Locomosa project. We are 6 partners, 2 from Denmark, 2 from Germany, and 2 from Italy. And what is the project about? We are looking at the system with a 2-tank molten salt storage system. We're purchasing electricity from the grid here, using an electric heater to convert the electricity into heat, storing it, and then supply steam on demand to industry. And the strategic objective is to demonstrate a low-cost molten salt thermal energy storage system. And the specific objective is, on the one hand, to demonstrate a high electric capacity, medium voltage electrical heater for molten salt. And the other specific objective is to demonstrate an additive manufactured heat exchanger with a novel heat transfer geometry. And the overall aim is to look at the system as a whole and reduce the system capex and opex costs through system level optimization. And this is exactly what I'm going to talk about today. So a few words on the motivation. Right now we have the situation that 1/3 of the global greenhouse gas emissions come from industry, and 2/3 of it is coming from emissions that are from supplying heat. And this is the one fact, and the other fact is that we have more and more renewable share in Europe in the next years. And with this, we have to focus, we have to force like how to match the intermittent renewable energy production and the constant demand of the industries. We already had a look at this Fraunhofer ISE energy charts beforehand. So what we can see here on the one hand side is the renewable energy production during 1 week. Then we have in black the demand profile from Germany, and in red the day-ahead market prices of Germany. And what we can see is basically when the renewable energy production is exceeding the demand, we have low prices or even negative prices, and then there is some periods where where we have where the demand is exceeding the renewable energy production. This is the periods with the high prices, and this is exactly the flexibility that we need. And there would be the solution of just using electrochemical batteries. But last year there was a project with 100 megawatt hours of storage costing 30 million euros with a lifetime of 10 years. And on the other hand, we have this molten salt storage technology used in CSP power plants. And when we have a look at the prices there, we have for a similar size of storage and a longer lifetime of 25 years plus, less capex cost on investment. So this is the main motivation. Yeah. So we want to have an economic opportunity with low-cost renewables, And we have the power to heat technology. Maybe you can mute yourself. And
Michael, can you mute yourself?
Yeah, thanks. Exactly. Now the question is how to integrate the system. So on the one hand side, we have the electricity going into the electric resistance heater with a high efficiency. We have a heat transfer fluid, which is solar salt for the presentation today, but we're also looking within the Locomosa project as other salt mixtures. This solar salt is heated up, stored in a hot tank, used on demand to produce steam for the industry. By this, it's cooled down, stored in a cold tank, and with this, we close the cycle. Main questions I want to discuss today is how to size the power to heat per storage system, what is the influence of the location of the storage system, and how could a backup auxiliary gas boiler influence the levelized cost of heat, and how does the electricity price forecast influence the levelized cost of heat? I have to admit that the numbers and figures I present today is not the final figures, but I think maybe still interesting to have a look at these results in order to come to something specific to discuss later on. Our evaluation is based on the levelized cost of heat. Because of the matter of time, I'm not going into detail of the calculation, but basically there's some lifetime considered, some financing factor of external funding, and also decommissioning things, and certain reinvestments, technology degradation rate. And then we have a number of cost functions in order to calculate the capex costs. And then we developed a control strategy for our system. So what we have as an input is the electricity market prices from the year 2023 in the reference case from Germany. Then we have a thermal demand profile, which is always 40 megawatt demand at 180 degrees, 10 bars, which is like a conventional steam grid at an industrial site. And we have a fixed threshold criteria in the first place in order to decide if we're gonna purchase electricity, if we're gonna charge our system, or if we discharge our system. Other signals that we have is the state of charge of our storage system and the hot tank temperature. And the outputs of this controller is then the power that we give to electrical heater and the mass flow rate in the system. So then there's different operation modes that our system should fulfill. Basically, we have charging plus steam demand, or we have a discharging where we have just steam demand, and then we have a base load where we do not charge our system, but we just fulfill our demand by direct electrical heating. Or we have no steam demand, and in this case we can charge our system without a steam demand, or we can lift up the temperatures of the hot tank in order to compensate for the heat losses over time. We do our simulations within our Fraunhofer ISE in-house system simulation software CallSim that was developed to originally simulate CSP power plants. This is why we all have all these models internally already existing. And yeah, then we have like a base case demand profile. We also analyzed other demand profiles, but this would be the base case, 5 days, 40 megawatt constant, weekends off. And then we have the electricity prices over the year 2023 in the reference case from Germany. And this can be downloaded from the Fraunhofer ISE energy charts, also for other European countries. So how does the system work then specifically? Here we have like the threshold criteria that I mentioned for the prices. All prices below this 50 euros per megawatt hours is considered at low prices where we charge our system. The prices above is the high prices to keep it simple in the first place. So when we have a look at our system, and we have high prices at this period, we're gonna discharge our hot tank level, or discharge, the hot tank level is decreasing. We discharging the system because the prices is too high. And when the storage is emptied, we're gonna operate our electric heater in a base load. And later on, when the steam demand is gone, we can shut off our electrical heater until a point where the prices are lower than the threshold. And just in this period, we can again recharge our storage system. So to keep it simple, basically. So the first case study we want to look at is the system sizing in Germany. So we analyzed different electrical heaters in the scale from 40 megawatt to 210 megawatt, and different storage capacities from 600 to 4,800 megawatt hours. Exactly. And with this study, we can compute this contour plots where we can analyze an optimized match of electrical heater size and storage capacity, and we end up with we can calculate the levelized cost of heat for this system for the prices of 2023. So we would, in this case, with the fixed threshold criteria, end up with a 200 megawatt heater and a 2,880 megawatt hour storage. So we could charge our system within 14.4 hours and discharge in 72 hours. But when we look at a more dynamic criteria to threshold criteria for charging our system, which is able to look 3 days ahead and then calculate the average price. If it's below the average price, we're going to charge. If it's above, we're going to discharge the system, basically. We can even further bring down the cost. So here, on the one hand side, without a storage system, just using the electricity from the market, we would have to have levelized cost of heat of 71.6 euros per megawatt hour. And with the dynamic threshold criteria, we can further decrease the cost to 62.7 megawatt hours. What is necessary to mention here is that this figures are not considering grid fees, as they are not fixed right now, and is still for the year 2023. So this is upcoming work for us. Having a look at different locations, we analyzed the European market and found out that for the year 2023, the Swedish market was the one with the highest price fluctuation during the year. And the Italian market was the market with the highest mean value. So we analyzed also these two markets and came up with the same contour plots. On the left-hand side, the Swedish markets, we come up with 50.8 euros per megawatt hours with the 50 euros threshold criteria. But this is the case without storage, and with storage, gonna just at the laser pointer, with storage, we end up with 45.5 euros per megawatt hour, and a smaller heater and smaller storage capacity. For the Italian market, when using the same threshold criteria, 50 euros per megawatt hour, we are not using our storage at all because the prices are just too high. So we're never charging our system, which is why without storage, the levelized cost of heat is even lower than with the levelized cost of heat. So this was a poor selection to stick with the same criteria here. But when we analyze again this dynamic threshold criteria of looking 3 days ahead, we can decrease these costs and end up with smaller storage systems, come to a point where the case without storage is not longer the cheaper one, but we actually have a usage of our storage here in Italy also, and we can even further decrease the costs for the Swedish market. Another study that we did was looking at the possibility to combine our power to heat plus storage system with a backup auxiliary boiler. So for the gas, we assumed that we have a cost of 42 euros per megawatt hour, which is already included in taxes for CO2 emissions. And then we can sum up basically that the money that we have to spend in order to fulfill our steam demand. And on the blue line would be our system without a gas boiler, just the power to heat plus storage. The orange line would be if we just go with the conventional system of a gas boiler, and the green line is if we combine both systems. So we can, on the one hand side, make the usage of the low electricity prices, but if there is periods with longer high prices, we can go for the we can use the gas boiler. So this is the combined solution. So here we can have an OPEX reduction by 55% with combining it even today. So this is again some specific criteria that we considered here, and we have to look deeper in this. But it looks promising that this might be already right now an interesting thing to do. Another study that I'm not gonna look into the detail here because a matter of time, but basically what we did was, on the first hand, we compared if I do not have the ability to forecast properly my prices, or if I can forecast my prices 1 day ahead or several days ahead. The logical wise, the operation of my system becomes totally different, because I can see right now that in a few days the prices are even higher than the prices that are exceeding my limit right now. And with this, we analyzed how is this affecting our money spent money that we have to spend on the energy to fulfill our demand. And we can see with longer forecasting periods, we can decrease this money, and we have a significant reduction. So our conclusion so far is that we now have our software toolchain developed to analyze different markets on a system simulation basis, and we can already come to some conclusions, even though the work is not finished yet. But the location defines the sizing of the system and the expected levelized cost of heat of the system, and a sensible dynamic limit for the electricity price purchasing or the charging of our system is crucial in order to achieve promising levelized cost of heat. And one interesting thing was that with power to heat plus storage, that we put aside an existing or to a conventional gas boiler. Even for the year 2023, we can significantly reduce the OPEX, even though the gas prices are still relatively low right now. They will increase in future, and with this, we can further decrease the share of the gas consumption and increase the electricity consumption here. It's becoming this more and more economical, interesting. And the other thing is that proper forecasting for a relevant period is important in order to have attractive levelized cost of heat. So what we plan on doing in the project further on is we will focus for sure on how we can reduce the levelized cost of heat with the system further. So on the one hand side, we will study potential OPEX reductions. So there we are looking at a more advanced dynamic price forecasting. And most importantly, we will study potential future electricity markets. So as I mentioned, it was just the year 2023 that we analyzed, but for sure for an investment, it's important to look into the future and into this lifetime of this 25 years and how will the prices behave in the future. And this And also, since we neglected this so far, is potential scenarios for future grid fee design in Germany and other Europe countries. Yeah. And then on the other hand, we will try to stick with comparing this solution with other potential technologies and the combination of with a gas boiler, and to see like how can we reduce step by step this usage of the gas boiler and still have attractive levelized cost of heat for potential user of this technology. Yeah, and on the other hand, we will analyze potential capex reduction, and there we're looking at other salt mixtures and materials and corresponding component sizes of the system. And with this, I'm done with my presentation, and I'm looking forward to your questions.
Hey, thank you, Julius. So do we have any immediate questions for Julius' presentation? Yes, there is one. Agustin?
Yes, I wanted to ask for your base consumption case, you assume 24 hours, 5 days a week, right?
Yeah.
If I can ask, I mean, I don't know, you probably don't have any idea, but if you were to change that demand consumption to 7 days a week, how do you expect the power to capacity relationship to change?
The storage most likely become more bigger, and normal wise, it's even more attractive to have the system doing the systems, okay. Because and even go for power to heat itself without a storage. If we have the weekend with us, we can just have super cheap electricity, use it directly, and then additionally charge the storage system. So it helps. So this is, yeah.
Okay. Thank you.
And we also did this analysis right so far. So yeah.
Any other immediate questions? Yes.
Maybe just
Herbert?
a small one. I understand that you have one full electric heating case. That is direct electric heating, or do you apply a heat pump there?
No, this is directly electric heating. So this is this case that we look at with the 180 degrees is more or less what the current technology of heat pumps is, not capable to do. Yeah. And on the other hand, like it's always like on this industrial sites, at a certain point you run out of waste heat sources that you can use. So you have to bring in additional energy somehow. So yeah.
I agree that say at one hand, so closed cycle heat pumps are still working at two process temperatures. I think in MVR you can already obtain them.
Yeah.
But maybe it would be interesting also for the economics to also compare to a heat pump case.
Yeah. Yeah, but this is always assuming that there is a waste heat potential, right? And if there is not, then it's not comparable. So it's a specific case that is difficult to compare with these other technologies, right?
Yeah, well, you could make an assumption here, I think, but it's
it's interesting to look at, and I'm already thinking about. I was already before thinking about it, but so far I decided not to do it because it's not like that you can place it everywhere with this heat pump.
Okay, thanks.
And Herbert, can you introduce yourself in your affiliation? Where are you coming from?
Sorry. So I'm from TNO in the Netherlands, and I'm there in a group working on, say, industrial heat. And mainly we do work on high temperature industrial heat storage and high temperature industrial heat pumps. So it's so we have the MVR and the compression heat pump in the lab, going to 150 in this case. Yeah.
we have also some heat pumps going up to 180 here at Fraunhofer ISE. So, but the other thing is the thing that is, I think, important here, that you need a waste heat source, and if you don't have it, then the heat pump is not an option.
Yeah, but in very many cases, I think you have some form of waste heat in industrial sites. So yeah, you could make an assumption there.
For a certain percentage. But like this is also like we have this 40 megawatt of, it's a generic 40 megawatt demand. And for sure, maybe there's an additional 5 megawatt demand that you can fulfill with a heat pump, and then you have still this 40 megawatt demand that you cannot fulfill because there's no heat source, because the energy is within your product, or
Okay, thanks.
Okay, and then we have a question from in the chat from Gerfried. Superheating via gas burner in absorption heat pumps. So just related to the heat pump discussion, some new possibilities perhaps. I don't know whether this is a comment or a question, actually.
Yeah, for sure, the steam could be superheated afterwards. If it's coming from a heat pump, superheating via gas burner is always, I think, not, it's a solvable problem from my point of view, but the heat pump topic is not my specific field of research. So.
Yeah, always interesting also to hear. I think a lot of our questions have been about possibilities of using new and other ways for power to heat, since we have very many technologies that can be used. But of course, our projects are now studying some options, and fortunately do have several options to study. But we can see that there is even more things to study for future. Okay, I don't see any other hands. So just to summarize this session, thank you very much for the presentations. We saw how the prices, actually, the electricity prices will impact the storage sizing, and this will then impact the flexibility that will come there. We heard already before that this is actually a moving target, so it's a bit sort of dynamic when we have changes and the big changes we are foreseeing. The prices are quite uncertain for future. And then again, this will impact what is being invested, what is the flexibility. Of course, we already see some flexibility coming from, that these are operated according to the prices. So at high prices, there is no charging. At low prices, there is charging. And already this will, of course, bring some flexibility, and also interesting to see this hybrid operation being studied, which is very relevant, I think, for the transition period when we still will use gas, but just reduce gas. And somehow I think that this kind of hybrid operation can also be a learning process for industry, sort of moving towards operation with storages and with other options for power to heat. So that was my summary for this session, and then I think we shall open the discussion session.